All right, guys, in this part of the lecture, we're going to learn about the pH scale. So what does pH refer to? Whenever we say P anything, what we mean is that we're basically taking the negative log in base 10 of that value. So for example, pH refers to the negative log of the hydrogen ion concentration. Similarly, the pOH would refer to the negative log of the hydroxide ion concentration. And finally, pKW would refer to the negative log of the KW. I'll go ahead and warn you that you will need a calculator that has the capabilities of calculating logs in base 10 as well as the anti-log. All right, so pH scale. Basically, the reason why we use a pH scale is that this scale allows us to express concentrations of hydrogen ions or hydronium ions in terms that are easier than the concentrations themselves. As we mentioned in the previous slide, the pH is calculated by taking the negative log of the hydrogen ion concentration, and this equation is very important. It's something that I expect that you guys will remember. Now, how does this actually help? How does it make it easier? Well, the pH scale changes by 1 for every power of 10 in the change in the concentration of the hydrogen ion concentration. And so, that doesn't sound very easy, but in fact it is. So for example, let's say that we have a hydrogen ion concentration that is 1.0 times 10 to the negative 4. That right there, if we go and take the negative log of that, we'll find that the pH associated with that is a 4.00. Then if I take a different solution that has an hydrogen ion concentration, let's say of 1.0 times 10 to the negative 5, that would refer to a solution that has a pH of 5.00. So as you can see, we can use the pH as an easier way to talk about the level of acidity of a solution, as opposed to using concentrations that are typically numbers like 2.3 times 10 to the negative 7 or something like that. Instead, I can use something that is going to make it easier for me to just look at the number and determine the level of acidity of the solution. In a second, we're going to talk about the scale of the pH, and that will actually help you see how much easier it is for us to think about the level of acidity by looking at the scale versus looking at the concentrations. Now, in order to, of course, we can use this equation in order to calculate the pH if we are starting from the hydrogen ion concentration. But what if we have the pH and instead we want to find the hydrogen ion concentration? Well, if you reverse this equation and basically solve for the hydrogen ion concentration, what you're going to get is the equation that I have here at the bottom, which basically says that the hydrogen ion concentration is going to be equal to 10 to the minus pH. This is also called the anti-log. I'll go ahead and kind of warn you that you need to be able to find a button on your calculator that has 10 with a little exponent. That exponent might be an X or a little box. That would be the key that you want to use in order to calculate this. This 10 to the whatever is not going to be the same key that you typically use to do scientific notation. So make sure that you're able to find it. I'll also go ahead and say that these same equations could be utilized for hydroxide ion concentration. So for example, I could take the pOH, that's going to be calculated by taking the negative log of the hydroxide ion concentration, as we just said a few slides ago. And similarly, I could say that the hydroxide ion concentration is going to be equal to 10 to the minus pOH, right? So the equations are valid whether we're talking about hydrogen ion, as in this case, or hydroxide ion, as here on the right-hand side. Let's see. Just to make sure that you find the key in the calculator and that you're able to do these calculations, let's say that we had a pH that was equal to 5.23. If this is the case, then when you go to the calculator to find the hydrogen ion concentration, you should do 10 to the minus 5.3 and that should get you the answer as 1.698, which in this case is going to be, let's see, we need 2 decimal places, so 2 significant figures, so 1.7 times 10 to the 5 molar. So please try it with your calculator and make sure that you know how to do these calculations. All right, the pH scale. So the pH scale is going to be organized in such a way that low values refer to acidic solutions, while high values refer to basic solutions. If we are talking about 25 degrees Celsius, then neutrality would occur at a pH of 7. So pH of 7 would be at 25 degrees Celsius. That would be neutrality. That would be a solution that is neutral. And as you heard in the previous video, a solution that is neutral is one where the hydrogen ion concentration is equal to the hydroxide ion concentration, and both of them have a concentration of 1.0 times 10 to the negative 7 molar at that temperature. Now, any solution that has a pH that is lower than 7 at 25 degrees Celsius would be acidic. And an acidic solution means that the concentration of the hydrogen ion is greater than 1 times 10 to the minus 7 molar, and that the hydroxide ion concentration is less than 1 times 10 to the minus 7 molar at this temperature. On the other hand, a basic solution is going to have a pH that is greater than 7, and a basic solution is one in which the hydrogen ion concentration is less than 1 to the negative 7 molar at this temperature, and the hydroxide ion concentration is greater than 1 times 10 to the negative 7 molar at this temperature. Now, the pH scale, notice that I have a 1 here at the beginning, but notice that the scale actually continues. It is possible to have pH values that are less than 1 and in fact less than 0. It just depends on the concentration of the acid. If you have a strong acid of very high concentration, then the pH can be 0 or negative. On the right hand side, you could have a pH that is greater than 14, in fact. That would be if you have a very basic solution that has a really high concentration. All right. So next, in this slide, what we're going to do is we're going to find an equation that is going to allow us to relate the pH to the pOH. That equation is going to be very useful to be able to go from one to the other in a simple step. The equation is here at the bottom. This is what you'll need to know in the end, but this is the derivation. So as we already know, the Kw, or the water dissociation constant, is defined as the product of the hydrogen ion concentration and the hydroxide ion concentration. And we said that at 25 degrees Celsius, this has the value of 1.0 times 10 to the minus 14. So I took that definition and I put it on the next line right here. I then took the log in base 10 on both sides of the equation. And remember that when you have the log of a product, that's the same thing as the log of one of the two things that are being multiplied, plus the log of the second thing that you're multiplying. Now, on the right-hand side, when you take the log of 1.0 times 10 to the minus 14, that actually gives you minus 14. Next, we need to remember that by definition, we had said that pH was defined as the negative log of the hydrogen ion concentration. So this right here seems to be the negative of this, right? They have the opposite sign, which means that this basically is summarized as negative pH. Similarly, we had said that pOH was equal to the negative log of the hydroxide ion concentration, which means that this is the negative of that. So basically I go and I call this the negative pOH. So now what we have is that negative pH plus the negative of the pOH is equal to negative 14. And if you multiply all of that equation by negative 1, you arrive at the equation that we have at the bottom, which is the fact that the pH plus the pOH is equal to 14. This is an important equation, again, because it allows you to calculate the pH from the POH or the POH from the pH. The way that you would use it would be by basically saying, okay, let's say that I want to calculate the POH. Well, the POH is going to be equal to 14 minus the pH, or if you're looking for the pH would be equal to 14 minus the POH. This is a very easy equation that you will find very handy, so keep it in mind. Okay, now significant figures for log calculations. This is a little bit weird, but I want you guys to utilize it. It's actually not that hard, but at the beginning it might be seen a little bit weird. So work with me here. So the rule is the following. The number of decimal places in the pH or the POH or the pKa or pKb or pKw, which we will talk about later. So then again, the number of decimal places is going to be equal to the number of the significant figures in the concentration. So decimal places in the pH or POH or pKa or P anything is going to be equal to the number of significant figures in the concentration. So look at the example here. This is my concentration. This is the hydrogen ion concentration. Sorry, this was supposed to be H plus, not H equal. So the hydrogen ion concentration is 1.0 times 10 to the minus 12 molar. It has two significant figures. Therefore, the pH associated with that is going to have two decimal places. Similarly, if you're starting with the pH, what you look at is the number of decimal places. This one has two decimal places. So when you go and you calculate the hydrogen ion concentration from that, you're going to have an answer that has two significant figures. If you're interested in finding out the reason for this, I'd be happy to tell you a little bit more. But basically, in summary, the fact is that these digits right here is what tells you about the, no, let me back up. These numbers right here tell you about the scale of the concentration. Notice that this is pH equal to 12. That 12 tells you about the scale, how big or how little is that concentration. While the digits after the period are the ones that tell you about like the minute concentrations differences that we're talking about, not the scale. Hope that makes sense. All right, let's go ahead and do an example. So the example is find the pH of a solution with a hydrogen ion concentration that is equal to 1.3 times 10 to the negative 5. And so we know that pH is defined as the negative log of the hydrogen ion concentration, right? And in this case, we know that the hydrogen ion concentration is equal to 1.3 times 10 to the negative 5. Now, depending on what calculator you have, in some cases you can type this exactly as I have written it here, but in some other calculators you might have to put in this number first. After that, you might have to type the log button, and finally after that you will have to change the sign of it. Give it a try with your calculator, and if you're still having a hard time figuring it out, please send me an email and I'll be happy to work with you on that. So after you plug this into your calculator, you should get the answer to be 4.89. Notice that in this particular case, our concentration had two significant figures. These are the significant figures. Therefore, our pH was supposed to have two decimal places after the period, right? That's important. All right, so now the question is the solution acidic or basic? There's two ways for us to think about it. If you go back to thinking about the pH scale, we said that at 25 degrees Celsius, the pH scale has a pH of 7 for a neutral solution, and the pH would increase, so 7 to 14 or beyond, for a basic solution. And on the other hand, to the left, we had smaller values of pH, let's say to 1 or beyond, and that was an acidic solution. Basically, any pH that was less than 7, if we were talking about 25 degrees Celsius, would be acidic, and any pH greater than 7 would be basic. So in this particular case, obviously this is less than 7, therefore that makes it an acidic solution. Another way to think about this is by thinking about the concentration of the hydrogen ions. We had said that at 25 degrees Celsius as well, a concentration that was less than 1.0 times 10 to the minus 14 was going to be a solution that was not 14, sorry. How do I erase? That's a great question. 1.0 times 10 to the negative 7, sorry, a hydrogen ion. Oh my goodness. Well, just to make sure that you don't forget about me, guys, here are my errors. All right, let me back up. So if we have a hydrogen ion concentration that is less than 1 times 10 to the minus 7, then that would be a basic solution. While if you have a hydrogen ion concentration that is greater than 1.0 times 10 to the negative 7, then that was a acidic solution. In this particular case, we have a concentration of 1.3 times 10 to the negative 5. That's bigger than 1 times 10 to the negative 7. So what we have is this scenario where we have an acidic solution, right? So that's two ways to think about it. Typically, thinking about the pH is a little bit easier. So I recommend that you get familiar with that. All right, the next example is to calculate the hydrogen ion concentration starting from a pH. Specifically, it says find the concentration of hydrogen ions in a sample of lemon juice which has a pH of 1.9. So as we know, we're going to do the inverse equation or the inverse log, where we take hydrogen ion concentration, set it equal to 10 to the minus pH, and therefore that's going to be 10 to the minus 1.90. Again, you need to make sure that you find the right button on your calculator. In some calculators, you are able to type it exactly as I have written it, while in some other calculators, you have to put in the 1.9 first, add a negative sign to it, and then push the 10 to the something button to get the answer. Anyways, in this particular case, we get an answer that looks like this in the calculator. It's a 0.012589254. But of course, we're going to take care of the significant figures. We said that if we were going from the pH to the hydrogen ion concentration, what we were going to look at was the number of decimal places on the pH, and that would give us the number of significant figures that we need. So we need two significant figures. The zeros to the left of the non-zero digits do not count as significant figures, so really we're looking at keeping these values right here. But of course we have to look at what comes after that. In this particular case, that 5 makes the 2 round up, so the answer should be written as 0.013. Or alternatively, I could have given it as in scientific notation as 1.3 times 10 to the negative 2, and the units in this particular case are molar units because our hydrogen ion concentration is in molar units. Is this solution acidic or basic? Well, just by looking at the pH, which is less than 7, that gives it an acidic solution or makes it an acidic solution. Similarly, the concentration of the hydrogen ions is greater than 1 times 10 to the minus 7 molar, which makes it acidic, of course. Part C is what would be the concentration of the hydroxide ions in this same sample. And there is two ways to solve this particular problem. One of the ways is to use the KW equation. Remember that KW is equal to the hydrogen ion concentration times the hydroxide ion concentration. Therefore, my hydroxide ion concentration is going to be equal to KW divided by hydrogen ion concentration. Oops, that is supposed to say hydrogen ion. And that's equal to 1.0 times 10 to the negative 14 divided by hydrogen ion concentration, which is 1.3 times 10 to the negative 2. And that gives us 7.8 times 10 to the negative 13. Alternatively, we could use another method, which is to use the equation of pH plus POH is equal to 14. And once we solved for the POH, then we can use a second equation that says that the hydroxide ion concentration is equal to 10 to the minus POH. In this particular case, it seems a little bit more complicated, but we could have done it if we can go ahead and do it. So for this particular case, I'm going to go ahead and use the first equation, solve for POH. So my POH is going to be equal to 14 minus the pH, or 14 minus the 1.90. The 14 is not going to limit your significant figures. You should be looking at the significant figures of the pH value that you're working with. So in this particular case, that gives us a 12.10 for the POH. And then I come to that second equation and I say, okay, my hydroxide ion concentration is equal to 10 to the minus 12.10, and that is equal to 7.9 times 10 to the negative 13, and that's molar units, of course, which is very close to the answer that we got with this other method. Either method would work. In this particular case, the first method was easier simply because we had already done the calculation on part A. All right. Next question is, what is the pH of a solution that has a concentration of hydroxide equal to 8.9 times 10 to the negative 9 molar? All right, so we have hydroxide ion concentration, which is here. And the question is, what is the pH of the solution? I hope that you guys go ahead and pause the video, give it a try on your own. Think about the two methods that you could use in order to do this calculation, and actually try both methods and then resume the video. All right, since you've already done it, you're just gonna check the answer with me, right? Okay. So first method would be to take the POH, or actually calculate the POH starting from the hydroxide ion concentration, and then from there find the pH. So to do this, first thing that we have to do is to calculate the POH, and that is equal to the negative log of the hydroxide ion concentration. That means that we're going to take the negative log of 8.9 times 10 to the negative 9, and that gives us a value of 8.05. Oops, 8.05. Notice that my significant figures are taken care of. I started with 2 significant figures, which means that I need 2 decimal places. From there, now I'm going to calculate the pH, and to do that, I'm going to use the equation that says that the pH is going to be equal to 14 minus the POH. So that's going to be equal to 14 minus 8.05. The 14 has as many significant figures as you need it to have, so just look at the significant figures here. You're going to need 2 decimal places, so that's going to give us 5.95, and we are done. The answer is right here. That was method number 1. The second method would have been to start with a hydroxide ion concentration and utilize that in order to calculate the hydrogen ion concentration by utilizing the Kw equation. Once we had the hydrogen ion concentration, then we could take that and convert it into a pH by using the pH equation that says the negative log, basically. The negative log of the hydrogen ion concentration. So let's give it a try. The first equation is our Kw equation, which is equal to the hydrogen ion concentration times the hydroxide ion concentration. We know the value of Kw, we're going to assume 25 degrees Celsius, and we know the value of the hydroxide ion concentration. We're going to use that to solve for the H plus concentration, which is going to be Kw divided by hydroxide. That's equal to 1.0 times 10 to the minus 14 divided by the hydroxide ion concentration, which is 8.9 times 10 to the minus 9 molar, and that gives us 1.1 times 10 to the negative 6 molar hydrogen ion concentration. We then do the second step, which is to convert that hydrogen ion concentration into a pH by taking the negative log. So the pH is equal to the negative log of the hydrogen ion concentration, which was the 1.1 times 10 to the negative 6, and that's going to give us 5.96. Notice that I had 2 digits on my concentration, therefore I'm going to take 2 decimal places. And the answer comes out to be pretty close between the two methods. The differences are always due to the rounding in the two methods, basically. All right, in this next slide, what we have is a table that lists a number of different substances with the relative concentration of hydrogen ions in those substances and the pH that would be associated with that hydrogen ion concentration. Notice that the exponent of that concentration is correlated with the pH. So a concentration of something times 10 to a negative 1 would be a pH of 1. 10 to a negative 2 would be a pH of 2, and so on and so forth. Here we have higher concentrations of hydrogen ion, which leads to a lower pH value. These ones right here are acidic on this side. Right here in the center, what we have is what we would know as neutral solution at 25 degrees Celsius, where we have a concentration of 1 times 10 to a negative 7 molar hydrogen ion concentration, and the same value for the hydroxide ion concentration, because remember that a neutral solution has an equal concentration of both of these. Now also remember that a neutral solution at 25 degrees Celsius has a pH of 7, and therefore it also has a pOH of 7, since the sum of these two is equal to 14. Then as we come down here, we have concentrations that are less than 10 to the negative 7, and therefore all of these concentrations here are going to be basic. Notice at the bottom that they give us the relationship between the concentrations. So the concentration of the hydrogen ion, regardless of what line you're talking about, is going to relate to the concentration of the hydroxide ions by utilizing your equation for Kw, right? Kw is equal to the product of the hydrogen ion concentration times the hydroxide ion concentration, which at 25 degrees Celsius is equal to this value. Okay. Similarly, these two numbers, regardless of what row we're talking about, are going to be related by this equation that says that the pH plus the pOH is equal to 14. So if you know the pH, you are able to find the pOH, or vice versa. The last thing is that I want you to look at the substances. So a lot of the things that we might like to drink, like milk or coffee or colas or vinegar or lemon juice, tend to be acidic. And some of the cleaners that we use at home, including borax and household ammonia and bleach, tend to be basic solutions. On the other hand, physiological fluids, such as human blood and interstitial fluids, are going to be neutral or near neutral. In summary, what we just discussed was ways to be able to calculate the pH. pH is defined as the negative log of the hydrogen ion concentration. If you have the pH, you can reverse this equation in order to find the hydrogen ion concentration by doing 10 to the minus pH. Again, there should be buttons on your calculator that allow you to calculate log and that allow you to do the inverse log. If you have a hard time finding those buttons in the calculator, send me an email, let me know what calculator you have, and I'll be happy to try to help you. On the other hand, we can apply that same equation for the hydroxide. So pOH is defined as the negative log of hydroxide ion concentration, and we could utilize the inverse equation in order to find the hydroxide ion concentration from the pOH. Similarly, we know that the sum of the pH plus the pOH is equal to 14 at 25 degrees Celsius, and that the Kw which is equal to the product of the hydrogen ion concentration times the hydroxide ion concentration, is equal to 1 times 10 to the minus 14 at 25 degrees Celsius. Finally, what do we use to measure pH? There's at least 2 different ways to measure pH. In the laboratory, you might have access to a pH meter that might look something like this. That pH meter has a probe that carries out some electrochemistry in order to figure out the pH, and it basically gives you a digital readout of the pH value, right? In this particular case, it says 7.38, so it's a solution that is nearly neutral, just slightly basic. On the right-hand side, we have pH indicators or pH paper. A pH indicator is basically a substance, a chemical that has 2 different colors depending on the environment. If it's in an acidic environment, it's going to have one color. And then if it is exposed to a basic environment, there's going to be a conformational change or a change in the molecule that results in a change in color. Those pH indicators can be impregnated into paper in order to generate pH paper. The picture that I have here is actually a substance that is obtained from cabbage. So you can generate cabbage juice, and if you expose it to solutions of different pH, you will see that the anthocyanin molecule in that cabbage juice changes color, and it gives you an indication of the relative pH of the solution. Again, if we take a pH indicator molecule and we impregnate it into paper, then we generate this pH paper that when we immerse that paper into a solution of different acidity, it is going to change color, and the color correlates with the pH basically. All right, finally, how do we select what pH indicator to use? So let's talk about number 1 here first. Which indicator from the right would you use in order to distinguish between a solution that is slightly acidic from one that is slightly basic? And I'm asking about the 3 sets on the right hand side, which I should have called 1, 2, and 3. So take a look at this, take a minute to look at what's happening in these 3 pictures. We're trying to differentiate a solution that is slightly acidic from one that is slightly basic. So what we're going to do is we're going to look at the 3 different indicators, methyl red, bromothymol blue, and phenolphthalein, and see which of those 3 changes colors very clearly at pHs that are relevant to a solution that is slightly acidic versus one that is slightly basic. All right, think, pause the video if you want. And hopefully you went ahead and ruled out the 3rd one, phenolphthalein, because if you notice, phenolphthalein is clear all the way to a pH potentially greater than 7. So I cannot differentiate at all a solution that is slightly acidic, like a pH 5, from something that is 7, and I really don't see a color change until I get all the way to 9, right? So I could totally miss a difference between something like 5 and something that is something like a 6 or 7 or 7.5 or 8. So I would go ahead and rule this one out. Now the other 2 indicators might work depending on your color sensitivity, but I would personally say that number 2 would work better. And the reason for that is that something that's slightly acidic means that it's slightly less than 7 for the pH, and something that is slightly basic is something that is slightly greater than pH 7. So what I want is to see a significant color change near 7. And as you notice, when we go from 5 to 7, there's a huge color change from yellow to green. And then as we go from 7 to the next pH level, which is 9 in this case, we go from green to blue. So there's a very clear color change, and I would say that this is the best case scenario. If we go up here, there's still a color change, but I personally have a little bit of a hard time seeing the difference between the pH 9 and the pH 7. So that's the reason why I would have chosen number 2. Now, second question. If a solution turns pink when we add phenolphthalein to it, what can we say about the pH of the solution? You can answer that either by looking at the figure right here of phenolphthalein or by looking at the plot here where it tells you what the color is at the lower pH, where it changes pH, and then what color it would be after that pH. So for phenolphthalein, it is colorless at any pH that is less than about 8 point something. And it becomes pink in this range, and then it would stay pink at a pH that is greater than this, right? So what can we say about the pH of the solution if it turns pink when we add phenolphthalein? Well, we would say that is a basic solution for sure, and more specifically that it has a pH that is potentially greater than 8, maybe even greater than 9, maybe, but greater than 8 for sure. All right, that is it for this video, and I will see you guys on the next set. Have a great day.